Okay, so I want to start by saying this. Do you remember we were able to find the area under a curve, but it was based on the Riemann sums, like all these rectangles we were adding up. So we started with RAM, rectangular approximation method. So it was based on that. But overall, we made it that it was the integral from a to b for whatever function this is. And that would add up all the rectangles to get the area under the curve. Okay. Well, what we're going to do now is just take that one step further. And instead of integrating to add up rectangles, we're going to move it to 3D. And we're going to add up areas, cross-sectional area of some shape. So like on this one down here, this example, it's like this parabola-like area shape. It just, two-dimensional would be like that. And all along here, we're adding up all of these parabola-like areas. And what we're going to do is have the integral of an area function, and it will add up all. So integral adds up many things to get the total. So here it was adding up rectangles to get the area, and today it's going to be adding up areas to get a volume. So this is volume by cross sections, and I want to show you some illustrations of this that are helpful. But basically what it is, here I'm looking at the box, is a of x is an area function. For our purposes, it's mainly going to be like a square or a triangle or a semicircle, some area function we know. It really could be anything like this. And we'll do that as well. It could just be area under a curve, like that. That's the area function. So area, calling it a of x, is cross-sectional area. And what we have to know is that's the cross-section anywhere along there. So it's not changing shapes, basically, right? It's this parabola-like shape all along here. Or I'll go back to this one momentarily. This one's squares, and it's a square all along there. There's building up squares on top of this shape. Okay, so it's going to be the same cross-sectional area all along. What we do is we go, there's two types. First we go perpendicular to the x-axis. Perpendicular makes the right angle. And so here's the x-axis on this one, y. So perpendicular is, they're going, like you can see the plane is going that direction, which would make a right angle here with the x-axis. So they're going that direction, and we go from A to B. But we will have, let's see what else I can say here. It's from A to B, yeah. So the volume is the area function, the integral of the area function from A to B. But we could go perpendicular to the y-axis. So I could do the same like parabola shape here, but it'd be going this direction. So notice if you go perpendicular to a different axis, it will be a different shape. What else do I want to say? Oh, they also could say parallel to an axis, but generally they say perpendicular to an axis. I'll let that out 1 second. And so here, again, this is like you take smaller and smaller of these like parabola areas, and you do the integral, and it's the entire.
I gotta go nurse my fingers bleeding.
And it gets you the entire volume. Andrew, what did you say?
For the y-axis, do you have to get new like integral values?
I would say new, but you have to get them. It's a dy function, like we saw the other day. It's sort of solved in terms of x equals something, and the values for your interval will be a y value. Because here, for the normal ones, the dx problems, it's left and right, a, b. But for a dy question, it's up and down, c to d. Any other initial thoughts? So let me show you a few illustrations. I got two here, and this is one I was already showing you here. So we're gonna take, you gotta start with some area, some 2D shape. And this one, it's this like parabola, kind of quarter circle. Oh, there it is a quarter circle, okay. They're gonna do square cross sections. So they're building squares on top here. It could be any 2D area shape. We're mainly gonna do squares and triangles and semicircles. But you just build it up, and you notice they get bigger because the curve went further back. So they just have, in order to fill up that entire area, they had to go further back. Okay. So notice if I went perpendicular to the y-axis, it would have been a shape built this way. Would have been different. Semicircles, triangles, other shapes would have different. It would be a different 3D shape. So basically, they're generating just squares all the way across there. I'm going to show you another one here. This is the region. It's this parabola. That's the base. And then what it's going to do is they're going to build it up. I think this one is squares as well. Let's see. Yeah, squares. Well, you can see it's a different shape this time. So they're building up these squares, and you can see the square expands. It's really the squares all along there. They're only choosing certain ones. But squares all along. There's a 3D shape. Let's see what they do now. Oh. kind of same thing. Oh, and then they can find the volume based on this function. So I have one other example here. This is a project that was made. So again, they just started with any 2D base area. So this one was like a rectangle and a triangle and like a semicircle on bottom. But they built it up with different shapes. That's what I like about this one. Here was semicircles all the way along. Here it was it was a triangular base area here. Sorry, everybody can't see that. But it was rectangles they built up along here. And then this one at the bottom, it's like a semicircle base. Looks like they did quarter circles. Quarter circle area all the way along. So, let's see if I can just leave this up.
Are we going to use numbers?
No, but we're just basically what they did here is they just found the volume over here. So let's see if we get out of this. So those are my 3 illustrations. Any questions based off of that right now? Anything to add? Thank you. Yes, let us. So we're going to be finding the volume of these solids. Solid is a 3D shape. We're going to find the volume of the solids. Now I added something here before we do one. It's very important to understand a very simple concept, but it sometimes gets lost. Oh, too far. Here, we'll do it over here. So I say very essential. Any point on a curve or a function is an xy point. So if I have this curve right here, that point is xy, some xy coordinate on a curve. That probably makes sense. But what we have to understand is this. I could go anywhere along here, along this axis, the y-axis. If I go over, that's x. Right? Because this point, if it's like 2, 4, it'd be right 2 on 4. So right x. So I went right x, anywhere along here, like there would be x. And if I went from the x-axis up, it would be y. So we have to know that anywhere on the curve is an xy point. So I said the distance from the x-axis up to the curve is y, height or vertical distance. And the distance from the y-axis over to the curve is x, the horizontal distance. Sounds pretty simple. You got to be able to know that. Okay, I start with the xy point on my curve, and that will help you solve these. Okay, let's try one. So we're going to find the volume of the solid whose base, so we have to start with the base region. Base is the region between the parabola y equals 4 minus x squared and the x-axis. So kind of as normal here, I don't have like 3 steps, but I'm going to draw a picture. So let me first do that, then I'll keep going here. Okay, so 4 minus x squared is You can use your graphic calculator if needed, but it's the parabola up 4 is a y-intercept, and it opens down. So roughly like this. So I wanted it bounded by that and the x-axis. Okay. So right inside here is our region. So I will temporarily do that. But that's the base region we're starting with. Just like over here, you know, sometimes there's the rectangle was the base here, a triangle was the base here. Vertical. Okay, so vertical cross sections perpendicular to the given axis. So this time we're going to do perpendicular to the x-axis. So anytime it says that, it means it's a dx problem. Okay, because we're going to be building it up this direction, and so our interval will be from left to right. Okay, and we're going to use squares. All right, so here's where I start, and I kind of do double or even triple substitution. I'll show you here. Okay, so I'm going to go up. The volume for this is the integral from a to b of an area function, a of x. So I need my integral, and I need to know the interval. Well, we're going left to right here, so I need these two. And I know this x dot is. So that is just where the functions meet, where 4 minus x squared equals the x-axis, which is 0. So a quick solve, add x squared to both sides, and then square root. So plus or minus 2. Okay. So that is our interval, -2 to 2. Okay, and then we're going to need an area function up here. So a of x. What is, and we're doing squares. What's the area function? What's the area formula for a square?
Base times
We need it in terms of one variable.
x. For wait, for a square?
Square.
Oh, just base square.
Yeah. Sometimes you can say like x over a square, they're all x, they're right angles. So it'd be, yeah, length times width or base times height, or x times x, which is x squared. I'm going to actually use, I don't know why I said x, I'm going to use s for side. So I'm going to use s squared. Okay, and then we said earlier it was a dx question. All right, so there's my first substitution. I just put in area formula. Yes, bless you. You're welcome. Okay, so I'm set up now, but in order to integrate, I need this in terms of the variable x. Okay, so here's where I'm going to kind of picture my squares, and then I'll be able to plug in what I know. So the squares are perpendicular to the x-axis, so they're going this direction. It's going to be pretty difficult. These are pretty difficult for me to draw, to visualize, but they're squares going across here. These are squares going across. It's almost impossible to draw these. I could change it this way. You know, it's just. So they're being built up three-dimensional on top. It's very similar to this one. It's basically that. It's hard to draw. Okay, so in any case, my square, I just need, I need to fill in what the side of the square is. And the side of this square that I know is from here to here, which is it's the base of the square. So imagine these are vertical on top. This is the base of the square there. And so that is the distance from the x-axis to the curve. That's why I said up here is very essential to know. The x-axis up to the curve is going to be y. It's an xy point on there. So if I'm going x-axis up to the curve, it's y. So I will fill in y for s. Because a side of the square is that from the x-axis to the curve. That's y. There's my second substitution. Finally, the last one. Well, we know what y is. Y is 4 minus x squared. So I'm putting 4 minus x squared in for y. Notice that it's also squared. So it's 4 minus x squared squared. And look at that. So the goal was to get it all in terms of an x variable. It is. And now this section is pure. Once you set it up, it's calculator. So I'll put this in. While we wait for that to load. So just again, squares. There's the area formula for a square. Here to here was the base of the square. That's the side that I knew. From here to here is y. And so I put that in. Okay, well, y is actually this. And I just put it in my calculator. So math 9, negative 2, 2. So parentheses 4 minus x squared. Again, don't count on me to do this. You need to practice and try this as well. 4 minus x squared squared dx. I like to change these to fractions, but you can leave it. You can leave it as decimal if you want. 34.13 pi. Repeating. Not pi. So you could leave it as that, or 512 over 15. So we're going to do 2 more to keep practicing with this, but first thoughts on this one. Anything I can answer? Yes.
I'm just kind of confused on how the whole base thing works with the
You're doing it.
I get it, but how do you you can't just assume that it's 2, right? I'm confused on
That you said 2? I'm sorry.
I know what if it was a rectangle or something? How would you find out?
You'd have to get in terms of one variable. So you'd have to know you couldn't do a rectangle unless you knew specifically the width was 3 times the length. Because then you could do the formula would be 3l squared for this one. You had to get in terms of exactly one variable. So you'd have to have a certain ratio you knew. But yeah, if it's 2 different variables, you couldn't do it. I don't know if that answered your question.
Yeah, I don't know.
If you want to ask more, feel free. But we'll do a couple more. Yeah.
So if this is y, then what part of the square is x?
Do you mean S? Because I don't want.
Okay, yeah, s.
Because I don't want. Yeah, that's why I'm choosing S, because X. So you said what part of the square is S? So you said all of them. So this square is that over there. So this is S, and this is S going up.
Okay.
They're all S, but the only one we know is this base one. That's the
and
only
that's
one.
y.
Yeah, it's the distance from the x-axis to the curve, which is y. Yeah. So you figure out which one you know. It's going to be the one that's on bottom there. Yeah, nice question. I try another one here, and we'll see. See if we get more familiar with it here. So let's go to B. I'm doing semicircles now. So let me just draw a quick picture. It's the same setup. That. Now we're going perpendicular to the y-axis. So here's the y-axis. So our semicircles are going here. This one, it's it's hard to draw. There's semicircles going across there. I'm just drawing a couple. I don't have to. Oh yeah. Pretty similar to this one. It's like semicircles going this direction. Hard to draw, but that's pretty decent. Let's see. Get rid of something here. So semicircles y-axis. So the volume is an integral of, let's start with, let's put the area formula in here. What's the area formula for circle? Pi r squared. So semicircle is half that. So the formula is half pi r squared. Or you could say pi over 2 r squared. Now this is perpendicular to the y-axis, so it's a dy question. That means we need the interval on the y-axis, the y values. So it's not going to be negative 2 to 2. It's going to be bounded by the x-axis in our curve. The bottom is certainly 0 for the y value. Then we got to find this top value here, which we already know. Yeah, it was, the parabola was up 4. So we didn't have to do any work for that one. It's just 0 to 4. Okay, so there's the setup. Now I need to get this in terms of y. So I'm going to replace r with something and get it in terms of y. So let's rewrite this. So I got 0 to 4, 1/2 pi. Okay, now here's what I'm going to replace r. So the radius of the semicircles is right there. Alright, like here's a picture of the semicircle, but the radius is from the center over here. There, over. What can I call that? From the y-axis over to the curve. Y-axis to the curve is over, because of point x, y. And the y-axis over is just x. And so I will replace r, I give myself too much room, I will replace r with x. And x, I can solve for up here. By the way, you can always, if you don't want to plug this, you can always go directly from this step to the third one here, like here to here if you want. So I need to solve for, I know y equals, what was it, 4 minus x squared. I need to solve for x and then plug it in right there. So I'm going to solve this for x. I'm going to subtract 4. Subtracting 4. Need to divide by -1 before I do square root. So I'll just change the sign. Negative y plus 4 equals x squared. Okay, and then I can do a square root of both sides. Okay, I can do a square root. Really going to be plus or, it's really plus or minus here. Right, when we do a square root and solving. But in a second, I'm going to square it anyways, so it's not going to matter. It's positive, so it really is plus or minus. I'll just leave it like this, though. Okay, so that's x. I put it up here. And then put this in my calculator. As soon as you get in terms of just y, then you can put it in your calculator. So square root of negative y plus 4. So again, I'll put it in, but it'd be good for you to practice on your own too. So 0 to 4, right? What was it? So you need 0.5 pi. Oh, actually, here. Yeah, that's right. I generally leave pi out. So I leave my final answer in terms of pi. Since the coefficient of number will not affect the actual integral, I can just pull the pi out. So I enter in it everything but the pi. So I enter the 1/2, 0.5, and then get the square root of negative y plus 4. Square root. By the way, for most of you with your calculator, you won't have a y. So you're just going to have to put x, but just treat it as y. So it'll work out the same. So negative x plus 4, and then is it all squared? All in parentheses squared.
Got any big plans for the weekend?
Are you not trying this on your own right now? There we go, 4. Yeah, be very careful entering then. And I haven't thought that far ahead. Oh, but I have our Reynoldsburg doubles tournament, so I'll be there. So it's 4, and I excluded the pi. So I gotta put it back in. Alright, so I'm gonna do one more of this type right here. But again, I wrote the formula for a semicircle. We had 0 to 4, and then I got the radius here to here. That was x. Now from the y-axis to my curve is x. And so I had to solve for x, put it in, and then just put it in my calculator. Yeah, go ahead, Sam.
If you put the pi in there, is that fine? It'll just be a decimal.
Yeah, the answer would be whatever 4 pi is, 12 point something.
Okay.
So you were saying like when you're making the little equation things, when you're solving for x, like we don't have to do that second step, just like solve for.
Right, you don't have to put x in here. You could just say, oh, like you already know it's the radius is x, and just go directly to this step. But I do it just to show you, because in a minute we'll see. X, it won't always just be x and y you're plugging in directly. It might have, we might have to adjust this ever so slightly. So, like in the next one. So let's set up part C. I say set up part A, we're going back to A, is perpendicular to the y-axis. Give myself a little room. So I have one more drawing of this. So let me start the volume. This one, it's the same setup as before. It was from -2 to 2. Oh, no, y-axis, I'm sorry. Y-axis, so we're 0 to 4. And we're doing part A, so that's squares again. S squared. But they want it as a dy question. So last time our squares were going here. So they're going build up there. This time we're doing squares. Again, the squares are sitting on top, but going top to bottom, really. So they intersect perpendicular to the y-axis. Okay. So that was the setup. We already have x and y solved for, so in a minute we'll be good with that. So I just need to find s. Just need to find s. So one side of the square. So if I look up here, I'll just look at this last one here. That's one of the sides of the square, right? Right there?
Yeah.
Okay. Now, it's not going to be just x, because we know, change colors here, we know from the y-axis over to the curve, that's x. A length of x. Don't worry about negatives here. A length of x. Well, this parabola is symmetrical. Mine doesn't look great, but this side is also x, a length of x. Yes, it's negative, the coordinate, but just for as a positive length, it's x. So here to here is x, here to here is also x. Therefore, the side of the square, s, is 2x. So s was 2x. That's what I'm talking about there. It's just a slight adjustment. Sometimes it's not exactly x or y. Yep. And now we already solved for what x was, so I'm just going to plug that in. X was over here. It was right there. It was square root of negative y plus 4. And I square it and calculator. So again, before I do that though, squares were going this direction. I like to make a picture. It can really help. Here to here to the curve was x. And it was symmetrical on the other side. If we didn't know it was symmetrical, we wouldn't know this one. So these were both x, and that represented the square x and x is 2x. 2. So notice I'm going to put in parentheses here. Start of parenthesis 2, and then square root of negative y, but I put an x, plus 4. Okay, then I close the parenthesis. It was squared. And then I should be good. And there we go, 32. Okay, and this one there was no pi I had taken out, so it's just 32. That's the answer. Good stuff. So after we've seen a few, let's process a little bit. Anything else I can answer right now? This one I think is a little more conceptual. It's not a lot of work, and it's not the work isn't too hard, but it's just you got to know what to plug in. That's the thing on these. Okay, let's flip it over and do another one on the back, where I don't use like a standard of an area, I guess. So we have to have a base area, and this one here it is. R is our region. Quadrant 1, let me pull some sketch here. Quadrant 1. Bounded by y equals e to the x, the x-axis, and y equals 4. So e to the x is just this function, a to the x function. Y-axis, and that one's just this. And let's see what else. Bounded by the graph y-axis and y equals 4. A horizontal line at 4. So that'd be somewhere like here. So basically on this one it wasn't as much here's one function. It was here's the region created. And then on that region we're going to build up some type of shape here. That's going to be squared, it looks like. So we'll get rid of that because I need to draw. Now first, like I did on this question, I compared it with what we did last section. So first I said, just find the area of this region. Okay, find the area between the curves. Okay, nothing with an area, nothing with volumes. Okay. So on this one, what's nice, we could do top minus bottom or right minus left. They're both good. And they're both just one interval. We won't have to split it up. Down here, though, we're going to be doing cross sections perpendicular to the y-axis, a dy question. So up here, I'm going to do a dy problem, just so I can keep it the same. I'll show you both. It's fine. So I'm going to do a dy. So I need to do right minus left. And so I need my interval on the y-axis. Okay, right minus left is the y interval. So it's certainly up to 4. Up to 4. But then I need this one right here. Okay, so I need where, what is that? E to the x, yeah. E to the x crosses the y-axis. So it crosses, e to the x crosses the y-axis when its x value is 0. And so we're going to get 1 here. It's just the y-intercept of a to the x type functions. Okay, and so we're going to get 1 to 4. And then I'm going to do, since this is a dy question, that I'm choosing to do it as, right minus left. The right function is the red, that was the e to the x, minus the left function, which is the y-axis. The y-axis has an equation of 0, x equals 0, just like the x-axis is y equals 0. So it's going to be e to the x minus 0. Okay, I gotta make one adjustment here. And that's a dy. Yeah, sorry about this. I made one error here. I need it in terms of y. So I actually need to get this one. This is the right one. I just need this in terms of y. So sorry about that. So here's my equation. I need it in terms, I need to solve for x in terms of y. So to solve it for x, there's one quick step. Just do an ln on both sides. And so it'll be ln of y equals x. So sorry about that. That's what goes here. I'm just going to write a new step. 1 to 4. So the right function is natural log y minus the left function, which is 0, or just leave it as nothing. Yeah.
So you don't put e to the ln y. Because ln y is x.
Right, yeah. I should have just had this directly solve for x, because it's a dy question. Yeah, so it needs to, I wasn't replacing it. This is just, should have just been natural log y from the start. Okay, then I'm going to put this in my calculator. 1 to 4, ln y. I guess I'll do it over here. 1, 4. I gotta put ln x. Yeah, so about 2.545. Just if you're curious, if you wanted to do top minus bottom, you could have. It would have been top, the green function, which is 4, minus the bottom function, which is e of the x. And then you would have had to get the left to right interval there, which would have been 0. And then you have to set these equal and solve for that one. And you would have gotten a decimal, or the natural log 4, whatever that decimal is. Okay, and you would get the same thing. So if you wanted top minus bottom, I did it this way, so we were already set for the next one. So there was a review of last section. Now let's combine it with this section. And so we're going to build up on here a shape. So the region R is now going to be the base of a solid. Each cross section perpendicular to the y-axis, so let's go this way, is a square. So my squares are going to be like this: square 1, square 2, square 3. That's pretty good.
Hey.
Yeah. Thanks. Building up, going back there. Okay, so it says find the volume of this solid. All right. It is a dy question, so we need the, we already have it up here, the y interval, so 1 to 4. Okay, then I'm going to need the area function. Okay. So the area function, if I have a region here, I can use what I did last section. Oh, I guess we're starting off with squares, sorry. I should do that stuff first. It's squares, which was s squared. But then I'm kind of already doing what I'm going to put in here. So let's say the side of a square is going to be, let's see if I can choose one of them here. Yeah. It's kind of hard to draw one after this. It's going to be right here, like the base of that. I know that one right there. So it's from the y-axis over to the curve, which is going to be x. And so right here, let me just do this in one step. I'm going to replace it with x, and I know what x is. We solved for it in the last question. X is ln y. Okay, so there's why I kind of jumped to that third step. Here's the first one. Then the second one was, all right, it's x. Plug what x is. It's ln y. Okay, and we just put in our calculator. So hopefully you notice a very subtle difference between finding the area under the curve, 1 to 4 of ln y, versus the volume for this one was 1 to 4 ln y squared. So that was the only difference. Okay, 1 up to 4, natural log, oh, actually in parentheses. Parentheses, natural log x. close parentheses squared should be good now, dx. Yep, about 2.59 seconds. And again, this would be volume, cubic units. And this area up here would be squared, so don't think they're that similar. Let's see if I can just finish up one last one at the bottom. What is okay. Any thoughts on that one? Let's try, yeah, I should be fine to finish up the last one. So the last one, just more examples with this different type of region. There's the region over there. You can see it's shaded. That's going to be the base of a solid. So region of the first quadrant bounded by the x-axis, the y-axis, and that line. What's nice about this one, they give it to you, and if you wanted a dy question, you'd solve it for x. If you want a dx question, you'd solve it for y. So you got to do some sort of real solve. Okay, if cross sections of the solid perpendicular to the x-axis are semicircles, what is the volume? I already have a picture. Let's go get our interval. So perpendicular to the x-axis is a dx question. And so we need the x interval, which is already kind of given for us, 0 to 8. Okay, so I'll fill that in. And then we go ahead and fill in, we're doing semicircles. So that's 1/2 pi r squared. And we want it to be a dx question. Or I mean, you can write pi over 2r squared. Okay, there's the setup. Let me go ahead and do, go and get this ready at least. I need r, I need the radius. Now let me make a little picture here. The semicircles are perpendicular to the x-axis, so they're going across here. They're going across there. So, here's the, you gotta be careful on this one. The radius is what we need, right? R. The radius is here to one side, right?
Yeah.
That's the radius. We don't know that, but we do know that from the x-axis up, that's something we know. So what I really need to do here is I need to put in, I won't know r, but I do know that from here to here is half, sorry, here all the way across is double the radius. In other words, the diameter. So what I'm going to have to do is, once I get y in a second, I'm going to have to cut it in half. So let's go ahead and do that here. It's a dx question, so I need to solve it for y. Rewrite it. Okay. So I need to solve it for y. So I'm going to subtract x from both sides. 2y equals 8 minus x, or negative x plus 8. And then divide by 2. So we'll get 4 minus a half x, or 5x, something like that. Okay. So what I'm saying here is I need the radius, but I don't have that. I have the red segment here is y, right, from the x-axis to the curve. Like, yeah, this whole thing is y. Well, I need the radius. So I need to cut my y value in half, because the radius here, the radius there to there, will be my y value divided by 2. So let's do it actually that way. I'll put in y over 2 here. There's a, or half y. You can say it like that. There's where I say sometimes it's this x or y, sometimes it's 2x, sometimes it's half x or half y. So my final step here to put in is just to put in what y is. Cassidy.
Sorry, it's 8:14.
Yeah. These things are off every couple of days. So I'm putting what is it? 4 minus half x in for y. Yeah, so I put that in for y, and that's what I put in my calculator. Again, I leave out pi in the calculator part. Well, what I entered the rest 10, I get 16 thirds.